So chapter 8, and this is dynamics in 2D. Technically in 2D and 3D, but it's still like in terms of 2D. Okay. So mostly like two-dimensional dynamics. Now, our goal for today would be to find the forces that make object to go around in a circular motion. So previously we talked about, let's say if you have an object of mass m, and let's say it goes around in a circular path like this of radius r. This is due to some kind of what we call centripetal acceleration. So let's say if this is the velocity, which is a tangential velocity because it's tangent to the path at any time. If I'm looking at this as a tangential velocity, then there are two types of accelerations. So one of them responsible for changing speed. So that acceleration is known as a tangential acceleration. And this is equals to then dv dt. So this is changes speed. Okay. So it's going to make it go faster and slower. But we also have something like, right? So this has to be sort of like tangential, so tangent to the path as well. Then we have centripetal acceleration, which always points toward the center. And this acceleration had an equation of speed squared divided by the radius r. So something like this we have already seen before. So this was then centripetal acceleration. Okay, I remember, right? So this equation assumes that speed is either constant or it's at the very specific instant of time. And speed is also can be calculated as the distance, which is if it covers one full cycle, it's then the circumference, so 2 pi r, divided by the time. And if the time is for one full cycle again, then that was the period t. So we can also kind of look at it from this point of view. So v equals 2 pi r over period. So those were the two equations we looked at before for centripetal acceleration or the motion, the kinematics of the two-dimensional motion. Now we're going to be expanding on this because what we have here is we are looking at motion where object is going around in a circle, and we want to know why it's going around in a circle. What gives us this acceleration? And obviously from the Newton's second law, we know that there has to be some kind of net force to give us acceleration. So it's that equation, right? Net force equals mass times acceleration. So it means any type of acceleration requires net force. Okay. So if there's a tangential acceleration, it's tangential net force divided by the mass. And if it's a centripetal acceleration, well, it has to be then centripetal net force divided by the mass. So this is sometimes easier to consider as a net radial forces, or for the radial divided by the mass. So the radial is you take the center of that circular path, and you then draw a line connecting the center and the object. So like let's say this line right here. And any force along that line, along that the radial line, is then a centripetal force. So centripetal force can be pointing toward the center. In that case, it's going to be positive. Or it can point away from the center. In that case, it's negative. That means any type of centripetal force, it's not a specific type of force, right? For example, tension can be a centripetal force. Gravity can be a centripetal force. Push can be centripetal force. It's just a category of the type of forces. But centripetal forces pretty much produce centripetal acceleration, which then changes the direction. And centripetal acceleration changes direction. There you go. And this equation for the centripetal acceleration is then the net radial forces divided by the mass. Because you can have one, you can have multiple radial forces contributing to that, to give you the centripetal force. Okay. Again, so remember, so any force, so any radial force, like R for the radial, is positive if pointing toward the center, and the radial force is then negative if pointing toward, or like, away from center, if away from center. Obviously, assuming radially, so RED radially for the direction. So radially toward or radially away will give us that particular centripetal acceleration. All right. So again, remember, feel free to raise your hand if you guys have any questions at any time. Use that raise hand option at Zoom, and you guys can ask me questions. All right. So then, in terms of what we have over here is that, like I mentioned, right, the centripetal force is a category of forces. So anything that can pretty much give us this centripetal force. Okay. So then one of the things we can do here is we can look at either that or just in general, two-dimensional, right? So for example, there's a net force equals mass times acceleration. So this is the general second law equation. And obviously what we have here is we can break it down into then net force in the x direction, means horizontal component of the net force, can be calculated from adding all the horizontal forces, right? And this is going to give you MA, where this is just purely horizontal acceleration. That means all the four horizontal forces give you horizontal acceleration. And all the vertical forces give you vertical acceleration. So this is kind of like a general two-dimensional, which we've seen this before, but let's kind of come back to this. So general two-dimensional net force. So the idea is when you have a change in motion in the x direction, this can only happen if there's a horizontal force or the collection of forces that are not balanced, divided by mass will give you then horizontal acceleration. That means if you have horizontal acceleration, that means at least in one direction, your horizontal forces are stronger than in opposite direction. Same thing with the vertical. So if net vertical forces divided by mass gives you vertical acceleration. So that means at least one or combination of forces, right, are not balanced. So there has to be non-zero net force in that direction to give you acceleration. Because, for example, simply by looking at kinematics 1 equation, so final velocity in x direction equals initial velocity in x direction plus horizontal acceleration times time. So you can see, right, in order for the velocity to be different, there has to be a horizontal acceleration. In order for there to be horizontal acceleration, there has to be some kind of imbalance of forces in a horizontal direction. Otherwise, if this is zero, then this is zero, and you don't change your motion. You are in dynamic or static equilibrium. Okay. So that means, you are looking at either just horizontal or just vertical, or both of those directions to be the unbalanced of forces. Then you have some kind of change in motion. Same way, right? So V final y equals V initial y plus AY times T. Again, just looking at even equation 1 of the kinematics. If this is non-zero, then you have a change in velocity in that direction. If this is 0, that means you have no change in motion in that direction. That means, if you have AX but not AY, then you only change your motion in X direction, but not in a Y direction. So you have to be kind of careful in terms of that. So for example, if it's a free fall, and this is 0, but this is not. Okay, so this is not 0. AY, and we know that AY is equals to, remember, negative G. And the reason it's equals to negative G, because if you have the net vertical forces equals mass times vertical acceleration, if the only force is the gravitational force, and then we remember that gravitational force then technically gives us then g as acceleration, and it's in a this is equal to then you can say, right? This is equal to then well, it's going to be in a negative j hat direction. And if I then say that the left side is equal to negative mgj hat, the right side equals m times ay. If I cancel the mass, then you can see why ay equals negative gj hat for the free fall. It just basically comes from this. All right, so the idea is we're going to start with this. And we have an example that I'm going to solve using this general two-dimensional or three-dimensional, right? Let's say net force, because I can easily come back and add net forces in a z direction equals mass times acceleration along the z-axis. So technically I can have that as three-dimensional as well. Just we don't necessarily do too much of with that, but we can technically get that as well. So all right, so let me know if you guys have any question about any of this. There's one example that we're going to go over that kind of deals with just a general two-dimensional motion, two-dimensional dynamics. All right, so let's look at then this example here. So you have a 500-gram model rocket is on a cart. There's a rolling to the right at the speed of 3 meters per second. The rocket engine, when it is fired, exerts an 8 newtons thrust on the rocket. 8 newtons, thrust on the rocket. Your goal is to have the rocket pass through a small horizontal hoop that is 20 meters above the launch point. At what horizontal distance left of the hoop should you launch? All right. So that means our goal here is to take the position where we want to launch to be 0. And then we know that when it's launched, there's going to be net vertical force, right? So you can write exerts there's an 8 newton thrust force from that. That means there's a F, let's put like TH for thrust of 8 newton J hat. And we know that at any time, there's also going to be the, a gravitational force that goes against it, right? F of G, which is then, negative mgj hat. So the idea is, as you launch the rocket, it's going to be, you can write kind of more or less undergoing through like a circular path like this. So if you kind of assume that this is in the part of like a overall circular motion like this, then instant when it's launched, you are giving it like an upward F thrust force, and then the gravity will be in opposite direction, F of G. And this is being, let's say, the center. So what you have here is you have then these two acting as two radial forces. Okay. So, and we know that net centripetal force, which is the net radial forces, this is then is equals to mass times centripetal acceleration. Centripetal acceleration, which is this particular, type of motion where the object is going to undergo sort of like a circular motion because of that. So, all right. So, since the rocket is going to be launched purely in a vertical direction, we can then assume that, let's say if I'm looking at the, X direction, mass times horizontal acceleration, there's going to be 0 because there's absolutely no horizontal force acting on the rocket at any time. So, from here we can conclude that there's no horizontal acceleration because there's no horizontal force acting on it. Okay, so this purely in a vertical direction, which then we can assume that to be the centripetal direction, radial direction, because of the curved path that we are undergoing, and then we can kind of translate that to be a centripetal force. Okay, because not always you're going to have a centrifugal force if it's a vertical motion, right? So it's just in this particular instant, it's, you have something like that due to the trajectory that is given to you. You can say, right? It's a circular, so like, let's say trajectory. All right, so what you want to do here is then you want to write things down a little bit. So we're going to take the position of the racket and a car at that instant, right, to be the origin. We are told that the mass is 500 grams. So we take this and we convert that to kilogram, 0.5 kilogram. So we write down in terms of what we know. So the known values are mass, then horizontal, vertical, and time initial to be set to 0. And then we know that initially the car is moving with some tangential velocity of 3 meters per second speed. Okay, so we assume that since it says that it's rolling to the right at that speed, we can assume that tangential speed is constant, so it doesn't change. So it's a constant tangential 3 meter per second speed. All right, so then we know that there's a vertical force, thrust force in upward direction of 8 newtons. And obviously, there's a gravitational force of negative mg, which we'll look at that. And since their initial motion was along the, horizontal axis, right? The initial vertical velocity is set to be 0 because the car initially moving only along this, a flat road, right? When it launches the racket. So there's initial velocity in the x direction, which is same as final velocity in x direction. There's no change in that. But in a vertical direction, velocity will change where we start initial velocity in the y direction to be 0 because there was no vertical motion to start with until, the racket is launched upwards from rest in a vertical direction. Okay. Also, we also told that going from taking this to be point A, then taking this to be point B, the vertical change in position from A to B, which we can call as a delta y, is 20 meters. So we have to go 20 meters above, you can kind of do this, right? So they have like 20 meters above the launch position. So that information we're given. So in a way, you can say that, y initial is 0 and y final here is 20 meters. You can also do that. Okay. What we're not given is what will be then this x final, and that's what we want to find. So how far away from that, the hoop where we need to launch the racket so that it actually, as it moves along this trajectory, it does pass through the hoop. If we're closer, it can go like this, doesn't. If you're too far off, then it's going to go like this, so it's not going to reach it. So our goal here is to calculate, and that's the beauty of physics, we can easily calculate that particular starting position where, if we know how, what is the launch thrust force and how much gravity is affecting, we can calculate this particular, let's say, distance from the hoop where it can be launched and successfully go through the hoop. All right. So we can probably ignore any type of air resistance effect. So our goal will be then to understand that what we technically want to find here is displacement, delta x. So the delta x is equals to, remember, is initial in x direction times time plus 1/2 ax times t squared. So for example, this is one of those equations that we can do to find it. Well, the idea is that since there is no x acceleration, this is 0. So then this is then equation that we need to find this delta x. And initial velocity in x direction is actually given to us. We even have that. It's 3 meters per second speed. So we know that. That means our goal is this delta x is equals to 3 meters per second I hat times time. Now, that's what we don't have. That means here, let's call this equation 1, which is the equation that I need to solve displacement. The only thing I need here is time, but we don't have time. So if we don't have time, then we know that the time is a kinematic equation, kinematic information, right? It's a variable. So I can use that to solve for any of the kinematic equations. Well, if I want to find then the time, I have to, since in the x direction, I have only one equation and I'm using that, and I don't have enough variables. I have to then go and look at it in a vertical direction. And in the vertical direction, equation 2 I can use is, it would be then delta y equals initial velocity in y direction times time plus 1/2 times vertical acceleration times t squared. I can use this equation to solve for time, because I don't have any initial velocity in a y direction. So this equation is simply 1/2 ay t squared. Delta y is an information that I have. So this is 20 meters. But at this point, if I want to solve for t, I also need acceleration in a y direction, which I don't have at this time. But then this is where the dynamics come into play. I don't have acceleration to solve for the time, because then time will be 2 times delta y divided by ay, and then this is square root. I don't have the time, acceleration, but now I can go into like dynamics of, let's say this part of the problem, and solve the acceleration using Newton's second law. So that's what we're going to do. So let's say we're going to then come back and say, all right, so what I have here is the instant that it's launched, it is given the thrust force of 8 newtons J hat. And it goes against the gravitational force, which is then negative mg J hat. So since we're given the mass to be 0.5 kilograms, and this is 9.8 meters per second, we can see, right, half of that 9.8 is then negative 4.9 newtons J hat. So this will be then gravitational force. So the net forces in a y direction will be then thrust force minus then the gravitational force. So technically as forces, right, then plus. And then here I can say, okay, so this is 8 newtons J hat minus 4.9 newtons J hat. And I can just calculate the net force. All right. So here I will get then, 3.1 newtons J hat as a net force in a y direction. Right, and from here I can see that those two are radial forces. So I can then use this equation to calculate acceleration, centripetal acceleration, where the net force in the y direction happen to be then my net centripetal forces. And this will equal to then m times speed squared divided by r, mass times centripetal acceleration. And since centripetal acceleration is v squared over r, so then it becomes m times v squared over r. So which means from here, technically then, there's a number of ways I can do. Here is, for example, here I can then solve for the acceleration, right? Centripetal acceleration. So centripetal acceleration equals 3.1 newtons divided by 0.5 kilogram mass. This should be 3.1 over 1/2, or 3.1 times 2. So 6.2 meter per second squared, J hat. So this will be then my acceleration. Again, so this part here is then dynamics, right? So you can see, right, I use dynamics to solve for the acceleration. And finally, I can then use this all the way, plugging it over there. So square root of 2 times 20 meters divided by then 6.2 meter per second square acceleration, and get time. So time should be 2.54 seconds. Let's say 2.5 seconds. I don't have enough space, but I can just write maybe a little smaller. There you go. So I got that. That means it takes 2.54 seconds to go from point A to point B. Now that I have time, I can finally go back to this equation, right, or to that equation over here, and solve for then the displacement on the horizontal, so 2.54 seconds. That means we can then calculate delta x, which in this case, 7.6 meters. That means we have to launch this 7.6 meters away from the hoop in order for it to successfully go through the hoop. There you go. All right, guys, let me know if you have any questions. All right, so let's go back. Right, so kind of modify this a little bit. So now think of it like this, right? So what we have here is, we can look at then, so we have this uniform circular motion. Uniform circular motion. All right, so generally then, if object specifically, let's say, goes along this vertical trajectory, something like this, right? So we have this tangential then velocity. In order for it to go around in a circular path, then as we said, right? So there has to be a centripetal acceleration. It always points toward the center. So then this will be like the radius r. Then this is, we can kind of like draw a line like this and call this a radial direction. So any force that gives us this centripetal acceleration has to be along that radial line. For example, if there's a force like this, perpendicular to that radial line, this doesn't contribute to the calculation of the centripetal force, which we'll see in a couple of examples. So then we can think of it like this, right? So for this particular type of uniform circular motion, right, specifically, so we have a radial direction, and we have tangential direction, and also direction, you know, into the page or out of the page. So basically in plus minus z direction. And again, that's our z axis. And that will be, let's say, into the page or out of the page, right? So in the plane of that. All right, so what we have here is, if I'm looking at that, we have then, in the radial direction, there will be no velocity, because we assume that the object is not going toward the center or away from center. It's always going to go along that red line, the circular path trajectory that I just have. So there is no radial velocity. That means it's not going to move in this direction. Okay, so it doesn't have that type of velocity. So there's no, so VR equals 0. But there's going to be tangential velocity, because, you know, this tangential velocity means that, you know, perpendicular to that radial line. Okay. And what we have here, generally, if you remember, right, we looked at the rotational motion. This was equal to r times omega. You can also look at it in terms of omega. We use angular variables. So then that's kind of what actually, let me put this here. So the tangential velocity equals r times omega. But there's also no motion along the z-axis. That means out of the page into the page, we assume there is nothing there. And when it comes to acceleration, we assume that because it's a uniform circular motion, there has to be some kind of acceleration in the direction of center of the axis. That means there's a centripetal acceleration is equals to v squared over r. And since it's equals to v squared over r, but v is equals to r times omega, I can replace v with the r times omega. This is also equals to r omega squared. Also can be equals to that. So centripetal acceleration also equals to r times omega squared. When it comes to tangential acceleration, it's zero because of this word, right? Uniform circular motion means that alpha equals zero. And if you remember, right, tangential acceleration was equals to r times alpha. And if alpha is zero, then tangential acceleration is zero. There's also no acceleration along the z-axis. This is also zero. So that means next we're going to be pretty much considering purely uniform circular motion. We then will come back at the end of the end of this chapter, end of this today's class, right, to look at non-uniform circular motion. You can also kind of look at that. So when it comes to then uniform circular motion, so we're dealing with, you know, this particular, let's say, table, right? There's no radial velocity, there's tangential velocity always, there's no z velocity, but in terms of acceleration, only radial or centripetal acceleration, but no tangential and no acceleration on the z-axis. Which means that if I'm then considering force from the point of view of the force, right? So then the tangential force, which is mass times tangential acceleration, is going to be zero. There's going to be no tangential forces. Then radial forces, then going to be mass times centripetal acceleration. Then I'm going to have this, right? M times v squared over r. So there will be net radial forces. And then we can ignore any forces along the z direction as well. Because according to this table, right, a t and az are equals to zero. So we can effectively ignore any tangential forces, any forces along the z-axis, and only concentrate on forces that are radial. That means, again, pointing toward the center or pointing away from the center. And or they have a component, you know, away or toward the center. Okay. All right, so for example, right, so let's say if you have object of mass m and there's a string. So that let's say if you use the string to rotate, right? So let's say imagine, right? So here's a string and here's someone holding this, and you just rotate this like that, like a helicopter, so like right? So it's just rotating like that. In this case, what you have is this will be then, let's say, the radial direction if the object is on the left side. And in this case, the only force acting will be tension in the string. F of t. We know that there's also gravitational force. But in case, right, gravitational force is not a radial force, it's not along that red line. So when I'm doing then net radial forces, right, or net centripetal force, then all I have to do is use tension only, because again, this is not along that radial line. That means only tension force gives you this centripetal, you know, centripetal acceleration. And v squared over r. Okay, so this is known as a horizontal circle. So generally, when you have a horizontal circle, gravity is not a factor because it's purely moving in a horizontal direction. So in this case, tension completely is along that horizontal direction. Gravity is not, so we can completely ignore gravity. In real life scenarios, which we'll, you know, you usually see in the experiments, that's not entirely correct. It's very difficult to keep object going purely in a horizontal circle. Usually, you do have a little bit of angle, and in that case, for example, right? So let's say probably one good example will be the canonical, you know, pendulum. So let's say you have a pendulum like this that's connected to a wall. and then you make this pendulum relative to this vertical axis. You kind of make it go around in a circle like this. It's still a horizontal circle. And what you have here is you have then gravitational force acting straight down, and then the tension force acting along the direction of the, let's say a string. In this case, none of them directly along this radial line, because the radial line will be relative to this. So this will be like, let's say this is the center. So this is the radial line. But I can see that gravity is perpendicular to the radial line, so it doesn't do anything. But the tension, if I look at then the tension, it can be broken down. Maybe it has an angle theta over here, which will end up with angle theta right there. So it has a component, right? So it has a component toward the center. So in this case, if I'm then looking at a force table, so if I do the tension force, by the way, the reason I'm doing F of t and not t, because here t can also be used for period. So I'm going to use t for period and F of t for tension, so that there is no confusion about that. So I highly recommend you guys use this for chapter 8. So you can write it's F of t and F of g. And what I have here is a tension. In this case, it has a component, right? So you can say it has a component. I don't know, use a different color. There's a component in this direction. So I break it down, right? It has that. And that's the radial force. That's what's going to give us centripetal acceleration. If theta is here, then that same theta is right there, which means that this particular component is in terms of sine theta, because if I take it and move it here, it's the opposite of the angle. And then cosine is in a y direction, y component. All right, so then this is 0, this is negative mg for gravity. There is no motion changing y direction, so there's no acceleration there. But here, then I can say it's mv squared over r, because along that radial line, right, in that particular plane, it goes around in a circular path. So then it's acting like a centripetal accelerator. This acceleration it gives us is a centripetal acceleration. All right. So generally, then what we can do, we can then use this, right? So for example, if I can set up these two equations, in one equation, then I have f of t sine of theta equals mv squared over r. In equation 2, which is in the y direction, is ft cosine theta equals mg. Let's say it's the vertical forces balance each other, but the horizontal force just one force, so it gives you acceleration. A lot of times in this type of problems, you want to solve for two things. Let's say usually you might be asked about what is the tension, or you might be asked what is the angle theta. And generally the best way to solve for this problem is to take this equation 1 and equation 2 and divide them by 1. So if I divide them, the left side is f of t sine theta over f of t cosine theta. F of t goes away, and I end up with tangent of theta. On the right side, the mass cancels out, and I have then v squared over rg. Okay. Then here I can just basically solve for a number of things. For example, I can solve for radius. I can solve for speed. I can solve for theta, right? Depending on what's given to you. So once you have this equation 1, equation 2, and you simplify to, let's say, this equation 3, then you can solve basically for any of those quantities. And once I, let's say if I need to solve for any of those quantities, then I have calculate some unknown from here. I can go back to equation 1 and 2, let's say, and solve for tension force. You can write equation 3 is tension independent. I don't need to know tension to solve for either radius or speed or theta. There's also equation 4 that is very useful in this context, where speed is equal to 2 pi r over period t. Then you also have this equation that can kind of help out, because let's say if I give you, 2 pi r over t. If I give you radius, but not speed, but I give you period, you can then use equation 4 to solve for speed, then move it back to, equation 3, solve for theta, move it back to equation 1 and 2, and solve for tension. Okay. Questions? This is one of the standards, examples that you usually see when it comes to this. All right, so this equation actually gives you kind of like the something we're going to be using in a little bit. So, but before looking at some examples, let's look at a couple of applications of this. So a couple of applications where we are going to be looking at using, let's say, the centripetal idea of the centripetal force. Okay, so the application of a centripetal force generally has two, useful applications in banked and unbanked road. So let's start with unbanked. Which is, in a way, what we mean by unbanked is a flat road. It's a flat road. So imagine, right? So let's say maybe this is part of a road. There's kind of flat like this, and you have, I don't know, you have a car kind of driving on this flat, flat road like this. Okay. So it is just everything is on ground, right? Ground level. So, but the idea is if the car wants to successfully make, in case, right, the car is not going straight, it's actually making a turn like this. So in order for the car to make a turn, there has to be a force directed toward the center. Okay. So, and one of the things we have here is generally if you have a car driving on a flat road or unbanked road and wants to successfully make a turn, the force that is happened to be what we call radial is actually a static friction force, right? Static friction force. So, and that's kind of what we have right now. I have an example that I want to, use it to kind of demonstrate this. So, how to use this type of problem. Okay, so here's what we have. Oh, actually, this is a example of what I talked about, like string. So I guess let's solve this and then go to the next one, which is then the unbanked road. All right, so let's say you have a 200-gram block on a 50-centimeter long string, swings in a circle of horizontal frictionless table at 75 RPM. All right, so imagine, right? So you have a table like this, and then here's a string, here's the object. It kind of goes around like this, along, on the plane of the table. Frictionless table means that, in a way, the two forces that we have is going to be normal. So there's a normal force, there's going to be gravity, and there is then the tension in the string. Okay. All right, so what I have here is, if I'm then looking at this two, I can say that, let's see what is given to us. So mass is equals to 0.2 kilograms. Radius is equals to 50 centimeters, so 0.50 meters. And then we're told that it's going around at the rate of 75 RPM. And if you remember, right, that's omega. Okay. So what we want to find is the speed, which means the tangential speed. And if we know that's basically r times omega, which we're going to solve that. And part B is asking for what is the tension in the string. So what is f of t, basically. Okay. All right, so at this point, we can see that part A is just easier. It's r times omega. So it's 0.5 meters times 75 revolution per minute, which we then convert for 1 revolution is 2 pi radians. And then 1 minute is 60 seconds. So we can actually solve it and get the velocity in terms of meters per second, because revolution cancels with revolution, minutes cancel with minutes, then you have meters times radians per second, but radian is not a real unit. So this is just going to be in terms of 3.93 meters per second. You ignore radian as a unit. All right, so let's see. So part B then is asking for the tension. Now, what I know about tension here is that tension is the centripetal force. So along this radial line, it's the only force, normal force and gravity are perpendicular to the radial line. So that means F of t is equal to mv squared over r. Then I plug in everything. So 0.2 kilograms times 3.93 meter per second divided by then the radius of 0.5 meters. Then I can solve for the tension. So, sorry, this is squared. So it should be then 6.2 newtons. Right. All right, any questions? All right, so this is the example that I was talking about. So let's look at this example here. So we have a 15 kilogram car that takes a 50-meter long unbanked curve at 15 meters per second. All right, so again, so think like, right, so this is the unbanked road. That means this is like a flat road, right? Kind of looking from the liberal side. And let's say, I don't know, here a car going such that at any point it has a tangential velocity to the curve, but it is going around in a circular path. And this is being the center. You can, let's say this is then this radius r. Now, in order for the car to successfully make a turn, it has to have a centripetal acceleration. And now we know that centripetal acceleration is due to some kind of centripetal force, net centripetal force. And that force happened to be then static friction for a car like that, making a turn like this. Again, so if I'm looking at then all the forces acting, I have then the normal force, which is basically perpendicular to the plane, straight up, and then gravity, which is straight down. So that means the only radial force is the static friction. Again, you kind of make a table here. Here you can say X component, or you can say a radial component. So the radial component, or you can say that, let's say Z-axis, right? Because in this case, it's going to be like sort of like a Z-axis. So we can say that this is 0, this is negative mg, this is 0, this is plus n, then this is plus f, because if it's pointing toward the center, it's positive. 0 here, and then net force is then, this is then net centripetal force, and these are two going to cancel each other. So equation 1 is then static friction equals mass times speed squared by radius. So it's net centripetal force equals just the friction force, and it equals to mass times centripetal acceleration, which remember is speed squared over r. Equation 2 then is normal force equals mg. Those two balance each other. All right, so what we do over here, for example, in this example, it says a 1,500 kilogram car takes a 50-meter long unbanked curve at 15 meters per second. What is the size of friction force on the car? Okay, that means I can see, right? So if I come back over here, I can say it's 1,500 kilogram times 15 meter per second squared divided by then the radius of 50 meters. And I can just easily solve that. It should be then 6.8 kilonewton. All right, so sometimes in problems like this, you might be asked to find the coefficient of static friction. In that case, let's say if you ignore that calculation, then if I come back to this equation 1 and 2, if I want to know coefficient of static friction, I can then replace this static friction with coefficient of static friction of normal force, then divide these two equations by one another. You can write normal force cancel out, mass cancels out, and I end up with equation 3, then gives me the resultant expression. So coefficient of static friction equals V squared over RG. So I end up with something like this. So here I can solve for the coefficient, or I can rearrange and solve for the speed, or I can solve for the radius. Any of those things can be solved by setting up your expression, equation 1, equation 2, then rearrange and solve, get expression 3 by dividing them, and then solve for any of the unknowns. All right, any questions? All right, so let's take a break. Let me see. So, all right, so let me back at 7:15. I'll give you about 12-minute break. So 7:15 p.m. we're gonna then resume. All right, guys, so let's go ahead and resume. All right, so now that we talked about banked road, sorry, unbanked road. So again, so unbanked road is something like this, right? So you have a flat road, so the car goes around flat road. And what we have here is the centripetal force is a static friction pointing toward the center of the curvature. Now, the idea of this is that the static friction that helps you to go around basically the successfully to make a turn is still, it's friction. And we learn about friction here is that friction depends on the conditions of the road. And for example, let's say in this equation, if I look at this equation right here, you can write, there's this static friction. If I kind of rearrange, speed is equals to square root of mu s times rg. So for this equation, right? So equation 3 can be simplified to this. And this gives you the condition for successful turn. That means in order for you to make a successful turn, you have to have a very specific speed, or let's say don't go above this particular speed. So for example, let's say here we took the, we were given 15 meters per second, right? So we were given 15 meters per second speed. For example, if I calculate this coefficient of friction, this was 15 meters per second squared divided by radius was 50 meters, then times 9.8. So this indicates that static friction here is roughly 0.5. Let's put it like this, roughly 0.5. Okay. That means that's the coefficient of static friction between the tires and the road. Now, the idea is that this 15-meter speed generally can be then considered maybe like the maximum speed or one of the highest you can have. Maybe you can go a little bit faster than that, but for example, if you go 30 miles an hour, sorry, 30 meters per second, or 25 meters per second, or 30 meters per second, that will be too much for the friction to be able to keep you on the road, and you then will slide off the road. So what we have here is, you can see that for this particular, if we would rearrange, we could then use this equation to calculate the maximum speed for this particular coefficient. So let's say if I do this kind of reverse engineer, if I did this, for example, 0.5 times 50 meters times 9.8, I would calculate 15 meters per second. That means if the road has this coefficient of static friction, so your designated speed would have been then 15 meters per second. If you go faster than that, then you have the risk of, going after all. The problem here is that this coefficient of friction of 0.5 is for dry road. So this is for dry road. What if I don't know, maybe weather conditions are a little bit different. Let's say, what if it starts raining or snowing, or there's an icy road? Then actually the coefficient of static friction will significantly go down. So for example, if it's raining, this coefficient can be maybe 0.3, or if it's icy, it can be even like 0.1, 0.2. And you can see, right, if I look at 0.2 even and calculate this, so 0.2, so square root of 0.2 times 50 times 9.8, I get a maximum speed of roughly 10 meters per second, which means if you are going with the same previous speed of 15 meters per second on wet road, then you can actually not be able to make a turn and, will slide off the road. So there's conditions, right? Weather conditions can affect, let's say, your particular effectiveness of the road to keep you, or the effectiveness of the friction to keep you on the road. All right. Now, that is why the engineers decided to design a different type of road where this weather condition can be technically negligible or even completely, ignored. So basically are either very small or completely negligible. So what they do here, they bank the road. That means there's a little incline, there's a little tilt. So the car is not going down an incline or up an incline, it's moving along that road, but the road itself is kind of what we call banked. So here's the question then. So if a highway curve of radius 500 meters is designed for traffic moving at the speed of 90 kilometers per hour, what is the correct banking angle of the road? Now the idea is when you are moving on a banked road like this, look at this. Let's say what we have over here is the forces acting on the car during this motion. You only have normal force and you only have gravity. There's no friction there. It's because then if you have the road correctly banked and you're moving at the designated speed, then you can move without needing friction to successfully make a turn. What allows you to make a turn is the normal force actually, because in this case, what we do here is we take the coordinate system such that, because right, this is the z-axis, and this is the radial axis, and what I have here is the normal force. Because it's banked a little bit, the road is banked, the normal force has a component, okay, right? It has a component along this radial direction. So the idea is then the normal force will be able to keep you on the road and you don't need friction. So you can make successfully, you can make this turn even if the road is completely covered with ice. All right, testing, right? However, you have to move at the speed that is required, right? So I'm going to show you like sort of like, let's say how this expression can be set up for this type of problems. So as I said, right? So at this point, what we have here is because the road is banked like this, and here's the angle theta, this is the one time we don't take the axis and tilt it. That's because again, we're not going down an incline or up an incline. It's just the road itself is banked, but the car is moving, let's say, on the road itself, right? So it's not going down an incline or up. So what we do here is we have then the normal force perpendicular and the gravity straight down. And what we do here is we take the coordinate system such that the radial axis is toward the center, you can write toward the center, and then the z-axis then the perpendicular to that radial line, which means the normal force end up making angle theta relative to the z-axis. So that means normal force is the only time ever you will see that normal force actually has a component. It's not purely vertical. So it's basically, in this case, it's going to have a component. All right, so if we use the force table, so you have a normal force and you have the gravitational force. So in this case, normal force, because the angle that normal force makes with the is a vertical axis or the z-axis, the radial component is then n sine of theta. And then the z component is then n cosine theta. Gravity is then straight down negative mg. The vertical or z-axis forces cancel each other. But this one is a centripetal force, and since it gives you mv squared over r. So two equations you get is n sine theta equals mv squared over r. This is then along the radial direction. So I'm going to put like this, right? So net radial forces. And equation 2, net forces along the z-axis, then this will be then n cosine theta equals then mg. They balance each other, but in a radial direction, nothing cancels the radial component of normal force, so you do have acceleration in that direction. All right, so what we do here, we again divide those two equations. And if I do that, the left side normal force cancels out, on the right side mass cancels out, which is also very interesting to see is that the mass of the car is completely, trivial. It doesn't matter if it's a small truck or big truck or motorcycle or a bicycle or whatever it is, right? They all can move at the same designated speed and be able to easily make a curve. Okay. Sine theta over cosine theta on the left side becomes tangent of theta. On the right side, then you have v squared over rg. And a very similar thing. And again, you can see, right, this equation gives you three variables: speed, theta, and radius. So you can kind of use this equation to solve for any of those unknown. In this particular example, you're given the radius, you're given the speed, and you want to find the angle theta. That means you take this equation, let's call this equation 3, and then solve for theta. So theta equals inverse tangent of v squared over r. Obviously, v cannot be in kilometers per hour. We have to convert that to meters per second. Okay, so in order for us to actually do the calculation. So, but once we do that, then we should be able to easily calculate. So let's say if we do velocity is equals to, so we are given 90 kilometers per hour. So we're 1 kilometer, 1,000 meters. And 1 hour is 60 minutes, 1 minute is 60 seconds, or 1 hour is 3,600 seconds, because it's 60 times 60. Kilometer cancel out, hours cancel out, and then you have meters per second. If we calculate this, we should get 25 meters per second. Then we'll come back here, we'll say 25 meters per second squared, divided by radius that was 500 meters, times 9.8 meters per second squared. All right, theta is 7.3 degrees for this problem. That means if you bank at 7.3 degrees and you're moving at 25 meters per second, it can be completely covered with ice. You can still successfully make a turn. All right, guys, let me know if you have any questions. All right, so then, so the next, what we have here is circular orbits. So let's talk about that. All right, so for this, you can imagine, right? So what we have here is, the idea is to think of it like, let's say if you have something that is projected, right, is launched. So we can have this flat Earth approximation. Again, just the approximation, right? So if we are looking at, let's say something, let's say maybe like a launcher that we had before, right? So if you launch it like this, it's going to go and come back and hit the ground. At this time, we assume that there's always going to be acceleration straight down, and it doesn't matter where it is, right? The acceleration always will be straight down, because flat Earth means acceleration always points straight down. Okay. But obviously, this is for small altitudes. So let's say 1 meter, 2 meters, 100 meters, 1,000 meters, something like that, right? So that means the height relative to the surface of Earth is relatively small compared to the radius of Earth. So then you can assume that acceleration due to gravity is always going to be, g. So the gravitational force is negative mg, and it's pointing straight down. So negative mg, j hat direction. But then if you kind of assume that if you start moving this height more and more and more and more and more, right? And I mean, let's say higher you go, let's say if you go here, then here, 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 as higher you go, then Earth no longer becomes flat. Then you start looking at the curvature of Earth, right? Higher you go, even more curved, more curved, more curved. Eventually, you can be high enough that when you look down, you see, you know, a spherical Earth, not, you know, a flat Earth. So this assumes that you are high enough that if I'm looking at this to be center and this to be radius of Earth, so the height is comparable. Here I can assume that the radius of Earth is much, much higher, greater than height, h. So I can just ignore this. But here you can't ignore that anymore. So then R, which is, you know, you can do like, you know, for the circle, you know, let's say if you launch it, right? What's going to happen is not, it's going to try to fall like it did over here, but as it try to fall, Earth going to curve under it, and then it's going to just go around like this. So then it's going to be basically orbiting Earth, you know, like this. So it's constantly in free fall, constantly falling, but Earth curves under it. So it just kind of goes like that. And again, what you have here is R is this distance over here, but that's going to be end up radius of Earth plus h, because we assume then the h is, you know, large enough that we cannot ignore that anymore. So R is just, you know, radius of Earth plus h. Well, in this case, then the gravitational force is equals to negative mg, but the direction not j hat anymore, right? But you know, it's radial. So then, in a way, we can do this r hat instead of I hat, j hat, k hat. We're gonna then have to do r hat. R hat is the notation for the radial. Okay, so in a way, toward the center. That means, you know, if it's here toward the center, if it's here toward the center, if it's here toward the center, if it's here toward the center. So it doesn't have a fixed I hat, j hat direction. It's always a radial direction, right? So kind of like radial, and something like that. Okay. All right. So then what we can do here is this, right? So we can say, all right, since my gravitational force, which is equal to then mg, is the only force acting as a centripetal force, and the centripetal force is equal to mass times centripetal acceleration, or mass times speed square over the radius r, then I can then say, all right, so then here I can cancel the mass and rearrange and solve for the orbit speed. And that will be rearranging this, so it will be square root of, you know, r times g. So in a way, it depends how up high it is. So remember, right? So this is then going to be a radius of Earth plus h times g, right? So this will then the speed, this tangential speed that this should have in order to go around in this particular orbit, and it depends basically on this radius r. Higher it is, right? You can see, right? Faster should be the speed in order to stay in orbit, right? So not to escape or not to fall. And then obviously, you know, we know that there's this equation where speed is equals to 2 pi r divided by the period t. And we can rearrange period is equals to then 2 pi r divided by v, right? And it will be then 2 pi r divided by square root of rg. Okay. And then one thing I can do here is we can kind of, you know, remove this from here, right? Because I can say t is equals to 2 pi r over square root of g times r to the power of 1/2. This is 2 power of 1. And then just kind of add them all together. And it's going to be then 2 pi square root of rg. So this will be then period for the orbit. Orbital period for so let's satellite or something like that. Okay. So this is kind of what we have. That means if you are, okay, so right, so the period of something is just basically, you know, depends on the radius. So this is for, like, let's say the period of a low Earth orbit satellite. So it completely depends on the distance. you know, and independent of its mass, something like that. So how far it will take for it to go around, it will be basically depending on this. All right, so now we're going to see that there are very specific type of, satellites that we want to have a period that matches the Earth period. Because let's say, for example, if you have a communication satellite, I don't know, say a radio station or a TV station that is used by some kind of Los Angeles, I don't know, let's say a radio channel or something like that, a radio station, you want that satellite to always be above Los Angeles, right? So you don't want to, broadcast when the satellite is above Los Angeles, and then half an hour later is, above, Vegas, and then half an hour later is above New York and things like that. Then you're going to lose signal and things like that. So what you want here, you want satellite to always be above, but Earth is, spinning. Then what you want satellite to also be orbiting such that it always keeps up with Earth speed. So these are known as a geosynchronous satellites. So, and I do have an example that kind of deals with exactly something like that. All right, so let's look at here. So communication satellites are placed in circular orbits where they stay directly over a fixed point on the equator as the Earth rotates. These are called geosynchronous. Remember, geo is named for Earth, synchronous, so synchronized with Earth. So geosynchronous. So they're called geosynchronous orbits. So the altitude of a geosynchronous orbit is 3.58 times 10 to the 7 meters, which is roughly 22,000 miles. So what we want to know here is what is the period of a satellite in a geosynchronous orbit, find the value of G at this altitude, and what is the weight of a 2,000 kilogram satellite in a geosynchronous orbit. All right, so well, the first part should be relatively straightforward. We can technically estimate it, but we can also calculate it. Remember, I gave you the equation, period is equal to 2 pi square root of r over g. All right, so take 2 pi square root of then 3.58 times 10 to the 7 meters divided by 9.8 meters per second square. So let's calculate that. All right, so I get 11,874 seconds. All right, so if I then take this where 60 seconds or 3,600 second is 1 hour. So take this divided by 3,600. Might I get something wrong? Let me double check. It becomes pi. Oh, okay. So sorry. I assume that this is the radius, but this is basically h. Sorry, that was my mistake. This is h. So that means we have to solve for the radius, which is then h plus radius of Earth. So 3.58 times 10 to the 7, and plus, then the radius of Earth is given right here, 6.37 times 10 to the 6 meters. Then the R is 4.22 times 10 to the 7 meters. There you go. Okay, so let's try again. Right. So what I get here is 13,000. But even that, if I divide by this. Oh, okay. Never mind. Okay. So the reason that particular equation didn't work, because t is equals to, I mean, it is a correct equation, r over g, but the problem with this equation assumes that g is not 9.8 meter per second square. Remember, g equals 9.8 meter per second square. Basically at the surface. And here I wrongly use this equation, but actually we're going to see in part B is that so technically acceleration is completely different. It's nowhere near this. So let's do something. Basically at this point we can just basically estimate, right? So since it's geosynchronous and Earth goes around one time during that time, that means that to be obviously 24 hours. Okay. So in this particular case, we can just basically take this as a fact, as a given, because it is rotating relatively to that. And what we can do now, we can actually use this as a known fact to calculate G for part B. So now I have this, I can then take that equation and rearrange and solve for that, right? So let's say at this point, I can take that t equals 2 pi square of r over g, t over 2 pi, then this is equal to square root of r over g, then takes a square both sides, so t square over 4 pi square equals r over g, then solve for g. So g is equals to 4 pi square times radius divided by period square. And I can calculate then g for that height. All right, so 4 pi square times 4.22 times 10 to the 7 meters. This is then divided by period, which is now 24 hours, where 1 hour is 3,600 seconds. And we square that. So then we should be able to then calculate this. All right, so let's see what we get. So 4 times pi square times 4.22 times 10 to the 7 divided by 24 times 3,600 square. Right, so I got 0.223 meter per second square. So as you can see, right, if you go to that's kind of, what is it, 10 to the 7, so that's 42 million meters above Earth's center, toward the center, relative to the center of Earth. Acceleration of gravity changes to 0.22, barely any acceleration there. So that's why, in a way, because everybody in the free fall, right? So they're already weightless, right? But the idea is that they are going to be, weightless. So the weight for part C is going to be, says, what is the weight of that? There's not going to be no weight, or that it's actually going to be weightless because there's no normal force in a satellite. So the satellite is technically in pure free fall. And in free fall, if you're in free fall, you are weightless because your acceleration is equal to the acceleration of gravity. So you actually feel weightless. But you can see, right, acceleration of gravity significantly decreases because of the height relative to the center of Earth. All right. Any questions? All right, so the last thing we have in this chapter is non-uniform motion. I guess we can probably skip the second break. I'll just, go cover this, finish it, and we can just finish it. We don't need to take a second break. So non-uniform motion. Okay. So for this one, imagine, right? So the idea is that you are going around in a circle, but non-uniform means that speed is no longer constant. That means you have a tangential acceleration as well, whereas dv dt, right? So let's say the velocity that you have at the bottom is different from velocity at the top. So dB is generally going to be much greater than the top. So non-uniform means you have changing velocity. All right, so generally this type of problems have sort of like two different types. So for example, there's what we call a roller coaster. So for something like let's say a roller coaster, let's say if it's a vertical, right? So if it's a vertical, there's like a roller coaster, and there's also let's say Ferris wheel type of thing, right? The difference here is for both of them, you have non-uniform motion technically, but in the Ferris wheel, what you have here, let's say here's somebody sitting here, and it's at the bottom. Let's say you go at the top. Well, you're still sitting just like that, right? So you're still sitting just like that. That means what you have here relative to the center. So you have, if I do like a radial line like this, your two forces are normal force up and gravity down. In this case, then you have equation set where normal force is toward the center, so N minus mg equals then mv squared over r, equation 1. And then this is at the bottom. And at the top, you have things reversed. So you have gravity toward the center and normal force up. They're still in this opposite direction, but this is mg minus normal force equals mv squared over r. Okay. So the normal force value, kind of changes, right? So let's say in terms of what you have over here, you have normal force always pointing straight up, where gravity always pointing straight down. It just, in one case, normal force is higher, is larger value than gravity. The other one here at the top, gravity is stronger than normal force because the force toward the center always stronger because you have to make a curve, right? Roller coaster is different because what you have here is, let's say, here's you at the bottom. But at the top, you are upside down. Right, so something like that. So relative to the radial line, so if you're looking at, let's say here you have a normal force, and you have then the gravitational force. So equation 1 is kind of still the same. So N minus mg equals mv squared over r. But at the top, what you have here, you have both of those forces pointing down. So at the top, you have the normal force plus mg. Again, both of them, let's say down, but remember, they're down at this top points toward the center. So both are positive. So N plus mg equals mv squared over r. So that's the main difference, right? So you can say here is the minus and here is the plus because both pointing in the same direction for a roller coaster. Where in Ferris wheel, they're still in opposite direction, but their magnitudes change. All right, so more or less something like this. So I do have an example where we can kind of, see something like this, right? But more or less, this is an example that you have. So you have a Ferris wheel, you have a roller coaster, and here we always assume that the speed is going to be speed at the bottom and speed at the top will be different. And usually at the top is less speed, at the bottom is higher speed because it has to actually be fast enough to kind of take you all the way to the top. Now, one of the things we have here is for equation 2, this is for the roller coaster. For equation 2, there's a special case. So this kind of calculates for the max speed, or sometimes known as a critical speed. So max speed or critical speed. This assumes that, let's say you have speed that is barely enough to get you all the way to the top, but when you're at the top, you're moving slow enough where you, like for a fraction of a second, you kind of out of your seat. So then normal force is 0. So then this equation N plus mg equals mv squared over r. So this special case for the max speed or critical speed, we assume that this is 0. So you kind of like for an instant off your seat. And then what we can do here, we can then use this equation where then mg is equals to mv squared over r, cancel the mass, and then your speed is equal to square root of rg. So this is known as a critical speed. That means anything this speed or higher than speed, you're good enough to come back. If you don't have, let's say, this speed or, basic, at least this speed, right? So if you have anything less than this, so let's say this is the curve, right? So you're going to go, but if your speed is less than critical speed, so you're not going to be able to reach the top and, basically you'll come back down way too early. So this is when the speed is less than critical speed. If speed is equal to the critical speed, you can then barely but able to make it and then come back. But then if it's not, then you kind of, unfortunately, we're not going to be able to make it. So that's why, when you're an engineer designing something like this, you need to know the critical speed for your roller coaster. Okay. All right, questions? Okay, so let's go back down here and solve for that problem. All right, so this is what we have. So a 500-gram ball moves in a vertical circle on a 102 centimeter long string. It says if the speed at the top is 4 meters per second, then the speed at the bottom will be 7.5 meters per second. What is the gravitational force acting on the ball? That's for part A. Now for part A, we don't need absolutely nothing to calculate this because this is just mg. So take, 500 gram times 9.8. Basically, it's half of 9.8, so it's 4.9 newtons. This is just simple enough. You don't need anything for that. Part B says, what is the tension in the string when the ball is at the top? You imagine, right? So this is the string, and the ball is at the top, moving with a speed of 4 meters per second, and there's a radius of 1.02 meters. Now, our goal here is to find the tension. Now, we know that at the top, here's the free body diagram for that. So there's a gravity straight down, but also tension down because that's where the string is, right? So the string, here's the tension, and there's also gravity. So the equation 1, let's talk about that. So this is at the top. It will be then the tension force plus the gravitational force together is the net radial force, and it's equals to mv squared over r. And this is the mv t for the top. So the tension force is equal to then the gravitational, so it's mv squared over r minus then the gravitational force. All right, so mass is 0.5 kilogram times speed of 4 meters per second squared, then the radius of 1.02 meters, and this is minus then 4.9 newtons. which is the gravitational force. All right, so if I calculate the tension I'm going to get here is 2.9 newtons. Okay. All right, guys, any questions? So then let's look at the part C. It says, what is the tension in the string when the ball is at the bottom? Well, for that, when it's at the bottom, the gravity down, the tension force is pointing up. So what you have here is then you have tension force minus mg equals mv squared over r. That means now the tension force is equals to mv squared over r plus mg. So again, 0.5 kilograms times now 7.5 meters per second squared over 1.02 meters, then plus 4.9 newtons. And you can see, right, what we get here, you get 32 newtons, much, much higher tension force than at the top. And it has to be much, much higher because it not only has to make the ball go all the way to the top, but it also has to fight against the gravity. That's why at the bottom, tension force is significantly stronger. In case, right, it's all over 10 times stronger. When at the top, tension doesn't have to be large enough because gravity already helping, bringing it down. So tension, you can even have a case where the tension is zero, the gravity can still bring it down. So that's pretty much, when your tension, the tension in the string, let's say at the instant kind of like goes to zero, so there's barely any tension, but you have enough speed where the gravity is able to successfully bring you down. All right, questions? Let me know if you guys have questions on this last problem or anything that we've talked about today. All right, guys, so then this is pretty much, that's all. So we finished the chapter. We're gonna go ahead and stop. Hopefully you're gonna guys have a happy 4th of July and have a good weekend, long weekend. So I'll see you all on Monday, right? So Monday at 6 p.m. sharp. All right. See you guys all on Monday. Take care.
Thank you. Have a good weekend.
You too. Bye-bye.